So we're going to pick right back up where we left off last time, and we're going to continue working some examples on how this power works and what does it look like once we add the calculus back in. So let's get started. Alright, so last time we were looking about what happens with a mass on a string as it goes around in circular motion. Now we're going to look at this figure. So this figure is showing two forces that are acting on this block. It's on a frictionless table, so there is no frictional force to deal with. So we want to know if we can figure out what does the power do to each force acting on the box at that specific instant. What is the net power, and is the net power changing? So we want to know what's happening when our speed is 3 meters per second, and just 3 meters per second. So our power definition. Power is your force dotted with your velocity. Now I see my direction of velocity right here. So my power for force 1 is going to be force 1 times the velocity cosine of that angle 1 between them. Well, one is going all the way to the right, the other is going all the way to the left. So that is going to be force 1, which is 2 newtons, times my velocity, which is 3 meters per second, cosine of 180 degrees. For power from the second force, that's going to be force 2 times the velocity, cosine of the angle between those two. So my force 2 is 4 newtons. My velocity is 3 meters per second. Now the angle that's between the force and the velocity component, you can see that that's just 60 degrees. So here I'm going to end up with cosine of 180 is a -1, so that's going to give me a -6. And this is watts, or joules per second. So cosine of 60 is 1/2. So this is going to end up with a positive 6 watts. So I have the power due to each force acting on the box at that instant, so big check there. What is the net power? What is the sum of all of the power happening at this time? Well, that's going to be power 1 plus power 2, which means we're going to have -6 watts plus 6 watts, which gives me a net power of 0 watts. Then our question is the power changing at that instant? So the power being 0 is telling us that the net rate of the transfer of energy, so how we are transferring energy to or from the box, that net rate of transfer is 0. So that means that the kinetic energy is not changing. So that means if the kinetic energy is not changing, our speed is not changing. Okay, so we're going to go ahead and we're going to look at our potential energy and what it means to have conservation of energy. So our potential energy, that is the energy that is associated with arrangement of systems of objects that exert a force. Now if we start looking at gravitational potential energy, which if you ever see me write this out on the board, you will see me abbreviated as GPE. Potential energy, the variable for that is U. Gravitational potential energy, we're looking at UG. Elastic potential energy, or spring, is US. So if you see me write this out on a board, you're going to see EPE, because elastic potential energy is a lot to write. So abbreviations out of the way. When we talk about gravitational potential energy, that is the energy that is in an object or stored within an object based on its position in a gravitational field. Basically, that is the energy that's associated with the state of separation of two objects that are attracted through gravitational forces. Our elastic potential energy, this is where that Hooke's law comes back in. That's the energy that we're going to associate with the with the state that we have is stretched or compressed for an elastic object like a spring or a rubber band. So when we are looking at the change in potential energy, that is going to be equal in magnitude but opposite to the work done by the object. So they're off by a negative sign. They are off by a negative sign. So then we start talking about conservative, specifically conservative forces. Now, conservative forces, these are forces we like. These allow complete recovery of energy. We can get all of our energy back. So if you think about conservative forces, it's like a bank that allows us to transfer our money from one account to another with no fees on it at all. We love conservative forces for that reason. They are forces that are operating within the system. It allows us to completely move all of our energy from kinetic to potential, or from potential to kinetic, back and forth as much as we want. Now, this is in contrast to something it's not listed here, but we need to realize exists, which is non-conservative forces. So non-conservative forces, we cannot regain all of our energy. That would be like transferring our money and they say, okay, thank you, that's 50 cents for every time you do that. Be like, but I kept my money there, I just changed it from one account to the other. Shipping and handling. So we could lose energy. We can't transfer everything over. So then we start talking about the change in gravitational potential energy. So if you remember from class, we had that nice little roll of duct tape. So if I have that roll of duct tape and I am going to move that duct tape up and into the air. So if I move that duct tape from one height up to another height, this is our change in y, we get that the change in our potential energy, final minus initial, is going to equal the force that's applied times how far we've done that distance. So this is going to equal basically mg times the change in our elevation, and it all ties back into work done to lift the object, to increase the separation. So if both the initial potential energy and the initial height are taken to be 0, then we get mgy. Now, not exactly a super easy formula to remember. So I'm going to show you another way to look at this. We've got the mass of the object, the acceleration due to gravity, and the displacement in the vertical direction. So our potential energy change is just mad. Okay, so elastic potential energy, we've looked at that in the last video. We were looking at how we had that triangle base and we could find the area under that curve. We could go from final to initial, and we would get this right here, this formula, as our change in our potential energy. So if I have a spring attached to a block, and we say, okay, this is its equilibrium position, this is its happy place, we say that that is xi equals 0. Then what we could say is that the change in potential energy, if we can say at this point our potential energy initial is 0, that means that our final potential energy is going to be 1/2 kx squared. And that x is going to be that final way we've slid it out away from its equilibrium position, or pushed it in past its equilibrium position. So enough formulas, let's do some work, or energy. So you are dropping a book to a friend, hopefully not letting anybody get hit with the actual book. They are on a ground a distance of 10 meters below. So if your friend's outstretched hands are 1.5 meters above the ground, we want to know how much work does the gravitational force do on the book as it drops to her hand. So this is 1.5 meters. This is 10 meters. Again, we start with a picture. Always start with a picture. And here we have a 2 kilogram book. So our first part, for part A, how much work is done by the gravitational force? Well, that's going to be mg times distance. Mg being the force due to gravity times our displacement. They're in the same direction, which is down, so we're going to have 2 times 9.8. And our displacement. Now, it would be all fun and dandy to go, okay, well, what is our displacement? Well, let's look. We are dropping it 10 meters down, but it's not landing 10 meters down. It's landing 8.5. So if we come in here with this calculation, this is going to give us 166.6 joules. So that is what the work is for the gravitational force. So how are we going to find the change delta U in the gravitational potential energy of the book Earth system during the drop? Well, remember what we said is that the change in potential energy is equal to negative work. So that means that the potential energy has dropped 166.6 joules. So yes, is that equation worth your time? Yes. So if the gravitational potential energy of the system can be taken to be 0 at the ground level, so our potential here is 0. Remember, there are times in our potential world we can declare. So here we're saying U is 0. So we want to know, what is U when the book is released? Okay, so if the book is released, then the potential energy is going to be MAD, or MGH. So that is going to be the mass of the book times 9.8 times 10. So that's going to be 196 joules at the top. Now, we want to know, what about when it's caught? So when it reaches her hands. So our potential energy is again going to be MAD, or MGH. So we've got the 2 kilogram book, 9.8 meters per second squared. And our height now at the point it's caught is 1.5 meters. So that's going to give us our new potential energy of 29.4 joules, which is pretty straightforward. Now we're saying, okay, hold on. Instead of letting U be 0 at ground level, we're going to let this be 100 joules at ground level. So we're going to let this ground level spot be 100 joules. So what does that mean for the potential energy up here? What does that mean for work? What does that mean for delta U? Well, the thing is that the work due to gravity, so our work due to gravity is going to be still mass times gravity, so that's the force that's coming down, times the displacement. It doesn't care where we start. It only wants the difference that it's traveled. So this is going to be the same, 166.6 joules. Okay, what about the change in potential energy? Well, that is going to be the same. The change in potential energy is still the negative of the work. If the work did not change, the potential energy did not change. At least the change in potential energy did not change. Now, what about the energy at this point? Well, the big difference between switching this from 0 to 100 is basically, it's like saying, okay, well, when you open your account at a bank, we're just going to auto put $100 in there for you. So if you deposited $5, you now have $105. If you deposited $20, you now have $120. So at the release point, our potential energy is going to be 100 plus what we calculated earlier. So that is going to be 296 joules. And at the hands, again, it's going to be 100, what our ground zero is. So this is going to be 129.4 joules. So take a look at this and tell me what questions you have.